Hi guys, welcome back to a new IMONST video. I apologize for the last long video, so I'll try to shorten the length of my following videos. And now let's look into junior problems 18 to 20 and senior problem 13 to 15. They are literally the same thing, it's just that the -5, okay? So in here, given a trapezium ABCD with sides AB parallel to side CD, something like this, let's draw it out. The two diagonals of the trapezium meet at E. So this is the point E where these two diagonals meet. And then parallel. So parallel means they never intersect each other. It is known that the area of triangle DAE, so this triangle, is three times the area of ABE. Determine the value of this ratio, the area of triangle BCD. So let me draw it here. To the area of triangle ABE. Now, this might be a very hard problem, but to simplify things, to make things easier to do, we would make our area of triangle ABE be 1. And then since we know that the area of triangle DAE is thrice the area of ABE, we just make it 3, right? Okay, so from here, what can we obtain? Now, let's just look individually at triangle ABD, as we can see here. So ABD, and then E is inside here. So we have 1, we have 3. Since both of them have the same height, I'm just rotating it. Okay, both of these have the same height. It is from here that we can know that BE over ED is equals to 1 over 3. Now, I need to talk a bit about the characteristics of trapezium, so bear with me for a little bit. We know that these two lines are parallel, meaning they never intersect each other. And then from here, from these two parallel lines, we would get these two angles to be the same. So angle ABD equals to angle BDC, right? And then we will also get these two angles to be the same since this is still parallel lines. So angle BAC equals to angle ACD. And of course, these two are the same because of vertically opposite angles. I do not need to explain this much. And then from here, we can conclude that this triangle AB, oh, I forgot the point E, sorry. Triangle ABE is similar. Use a wave sum to represent similar. Is similar to triangle CDE. Okay. So A corresponding to C, B corresponding to D, just E. And then from this we can kind of derive same lengths. So we know that from here AB over CD is equals to, say, BE over DE, right? Which is what we see here. B over DE is equals to B over ED. Is equals to, what is this? AE over CE, which is equals to, as we can see here, 1 over 3. This is 1 over 3. So if this length is x, then this length is 3x. If this length is y, then this length is 3y. We do not need to know what exactly x and y are. We just need to know the specific ratio. So let's draw it. So let's write it down here again. So this is some y, and then this CE is some 3y. BE is some x, and then DE is some 3x. Now, from here, since the heights are the same, so it's just the problem of the ratio of the bases. Same goes with the other triangles inside here. So let's take a look at triangle ABC. ABC, something like this. Then our point E would fall somewhere here. Since this is a y, this is a 3y, and then this area is 1. We will get our triangle BEC. So yeah, BEC to be 3. So this one's area is also 3, just a simplification. And now finally, we look individually at triangle BCD. So we look at BCD, something like this. Then E is in the middle again. Now, so BE is x, and then DE is some 3x. So we know that the area of triangle BCE is 3. So since their heights are the same, something somewhere here. So the area of triangle DCE is 9, as we can see here. Now, I would like to introduce a notation to denote area, which is this. So it's a medium bracket. So if we use a medium bracket and then say something BCD, right? This is to denote the area of this, I don't know, polygon or triangle BCD in this case. So the area of BCD I can use this one to denote, and then the area of ABE. Since we have a numerical value, things are easier for us to count. So BCD would be 3 plus 9, and then ABE would be 1. So this ratio would give us 12, and this is exactly the answer of problem 18. So I hope you guys understood my explanation. Now let's move on to problem 19. Now, problem 19 is a bit up there. In a class of 100 students, there are A females and B males, where 0 is smaller than or equal to A, and then A is smaller than or equal to B, equals to 100. Now, the sum of digits of SA is SA, and the sum of digits of B equals SB. And then if SA plus SB equals to 19, how many possible values of A are there? Now, at first you might be wondering, oh, let's try a few numbers and then let's see. So maybe 7, 3, and then 2, 7. Okay, the sum of digits for this one is 10. The sum of digits for this is 9. Then, oh, 19. Yeah, correct. Then, oh, then let's try another one. So 67 and 33. So this one is 13, and then this is 6. And then this would be a 19 also. Then you would be thinking, wow, all 100 of these must have 19. But you're wrong. Now, I would like to introduce a more systematic way of counting. So we would have, okay, do you recall your primary addition way? So will be the tens digit will be here, and then the ones, the units digit will be here. So let's do something like this. Since we have A and B used, we'll just use C, D, and E, F, right? Would add up to 100. Okay. Now, of course, there are sections of say. So this one would be A and this one would be B, right? So if say A equals to 100, and then the next one, then B would certainly be 0. It's 100, but the sum of digits is just 1, so this is not possible. And then vice versa. So if B is 100, A is 0, it's also not gonna work. Now, so we would have something like let me think. We will have our C's and E's to range somewhere from 0 to 9, right? Okay, because it can be 1 plus 99, then 2 plus 98, all the way until, say, 67 plus 33, and then 69 plus 31, blah, 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 all the way up to 99 plus 1. So all of these are either 1 digit plus 1 digit or 2 digit plus 2 digit, right? So for A or B equals to 100, we have covered that, and that is not going to work. So normally we would have this one. Okay, so normally we would have let me think what I need to say. Sorry. Okay, 5 seconds. Since we will have, observe D and F first. Since we have D plus F equals to some 0, and then our D plus F max, because the maximum is both D and F being equal to 9, since they are digits, they are not numbers, is 18. So what are integers that are smaller than 18 that end in 0? So non-negative, of course. So you would have either 10 or we would have either 0. So let's look at both of these cases. There are no other cases, okay? So again, we will need to divide this question into cases. So case 1. D plus F equals to 0, okay? If D plus F equals to 0, then C plus E equals to 10, and then as A would be C plus 0 equals to C, and then as B, as we can see here, so this is as A, just C plus D, then as B would be E plus F, as B would be E plus F equals to 0 is E, and then C plus E equals to 10, so this would not work. So D plus F equals to 0 would not produce any cases, so not applicable. Now let's move on to case 2. Okay, D plus F equals to 10. Okay, since D plus F is equal to 10, it means that 10C plus E, because C0 means 10Cs and E0 means 10E, equals to 90, which means C plus E equals to 9. So as A here would be a C plus D, and then as B over here would be E plus F, and then we would have this one plus this one, so these two add up to become 19. So we will need to count from all the numbers from 0 to 100, how many of these would have D plus F equals to 10. So we will have 199. Okay, 199, 298, all the way, okay, 991, 1090 does not work, as we've said before. They cannot be in multiples of 10. So we'll just, as you can see here, we do not need to invest in the effort of counting every number, right? We know that multiples of 10 do not work. Multiples of 10 won't work, so we just need to count the non-multiples of 10. So out of these, so from 0 to 100, don't be fooled, there are actually 100 numbers. And then you need to remove the multiples of 10. So 0 is also one of them. So 0, 10, 20, all the way to 100. So there are 11 of them. So how many possible values of A are there? So, there will be 90 of them. So this will be the answer. And of course, again, I hope that I explained it in, I don't know, simple English, not really simple, but understandable English, okay? Now for the last question, problem 20. A number is said to be k good if the number can be expressed as a sum of k consecutive positive integers. So for example, 27 is 2 good and 3 good, since, as you can see here in the title, or in the problem. Now, find the smallest number that is 2 good, 3 good, and 7 good. Now, we can, okay, so let's try. Let's discover the properties of any 2 good, 3 good, and 7 good numbers, okay? So for 2 good numbers, it will be in the form of sum a plus 1, right? Which is, because both are consecutive, so it'll be 2a plus 1. Since a is an integer, this means that any odd integer can fulfill the status except for 1, because 0 plus 1, 0 is not a positive integer. So all 2 good numbers include any odd positive integer larger than or equal to 3. Okay, so these are the how to say, kind of like characteristics of 2 good numbers. Now let's look at 3 good numbers. Okay, so 3 good numbers can be expressed in the form of something like b plus 1 plus b plus 2, right? So this would be something like 3b plus 3, which if we can take the 3 out, we will get something like 3b plus 1s, okay? So this obviously is a multiple of 3. So in conclusion, we can say that any multiple of 3 is a 3 good number, okay? Any multiple of 3. Of course, again, since b is at least 1, so we would have any multiple of 3 larger than or equal to 6, because 3 is 0 plus 1 plus 2. 0, again, is not a positive integer. Now, 7 good, right? 7 good numbers would be something in the form of c plus 1 plus c plus 2. You can take in the effort, so I'm just writing stuff right here. Plus c plus 4 plus c plus 5, and finally plus c plus 6. So we would have 7 c's plus, you just do the addition yourself, 7c plus 21, and then you find that 21 is actually multiple of 7. Then so you just take the 7 out, you get 7 c plus 3's. So from here, we can conclude again that any multiple of 7 is, no, what multiple? multiple of 7 is a 7 good number? Of course, since C is larger than 0, so any multiple of 7 should larger than or equal to 7, 1 plus 3 equals 28, will fulfill the conditions of being a 7 good number. Now, since we want this number that is 2 good, 3 good, and 7 good, now we have found the conditions. So it must be an odd number. It must be a multiple of 3. It must be a multiple of 7. So since 3 and 7 are co-prime, the lowest common factor, the LCM, is 21, and then we just find multiples of 21. And then, of course, since it's odd, so it will be 21, 42, 63, 84, 105, and such. Okay. Since they're odd, so 40, 42, 84, 126, and the like are eliminated, so we're left with 21, 63, 105, and such. Okay, so is 21 a 2 good number? Of course, since it's odd and then it's larger than 3. So is 21 a 3 good number? Of course, it's a multiple of 3 and it's larger than 6. But is 21 a 7 good number? No, because it's not larger than 28, because we want our C to be a minimum value of 1. So 21 is eliminated. So let's look at 63. Yes, it is an odd number. Yes, it is a multiple of 3 larger than 6. And yes, it is a multiple of 7 larger than 28. So 63, apparently, no. 63 is the answer to problem 20 in this case. It is the smallest number that is 2 good, 3 good, and 7 good, as you can see here. Okay, so this is how you solve problem 20. Of course, there's a much shorter way to solve this. But I want to convey my way of explanation to everyone so that everyone understands. So, of course, if you do not know what LCM is, it's the lowest common multiple. Go check it out on the web. And this is all for the junior section. For the senior section, there are like 5 questions left. So we'll deal with them one by one slowly. And we'll see you guys in the next video. So, ciao!